Okay, so good morning, everyone, and welcome to another exciting event from the Montreal NLP Consortium Meetups. In today's event, similar to the other events, we have three exciting talks that we're really looking forward to watch. And the presentations would be each one 25 minutes, followed by a 10-minute period for the question and answering. And the first presentation will be by Malik Altakrori, who is a PhD student at McGill University and Mila, and is going to present his talk on authorship analysis, discussing identification versus anonymization. The second talk will be on the topic of adapters, which is a relatively new approach and exciting one for transfer and continual learning. And we will be joining us from Germany, Jonas Pfeiffer, who is a PhD student at Technical University of Darmstadt and is going to present his talk on the topic of adapters and transformers, a new paradigm in transfer learning. And last but not the least, we will have a talk by Dr. Jian, who's a professor at Université de Montréal and the Rally Group, who is going to present their work on VGCN-BERT, which is an approach for enriching the BERT embeddings with graph embeddings. So without further ado, we'll move forward to the talks. Before we actually start, I would really appreciate if everyone keep their cameras and their microphones off during the presentations by the speakers so that everyone can enjoy the talks. So I'm passing the podium to Malik from Mila for his talk on authorship analysis, identification versus anonymization. So Malik, the floor is yours.
Thank you, Hassan. Thank you everyone for having me. Just quickly share my screen. Okay. How's the audio first? Am I too loud? Is it good?
No, it's good. It's good.
It's good. Okay. So my name is Malik Altakrori, and today I'm going to be giving a quick talk about authorship analysis, identification, and anonymization. So I'm going to start by introducing the team. So this is me, and I'm co-supervised by two professors at McGill, Jackie Chung and Benjamin Fung. Both are Mila members, and Jackie is in CS, Benjamin is in School of Information Studies, but he's an associate member of CS as well. Some of the work that is going to be presented is done by two former students of Benjamin. Stephen Ding, he was a PhD student and now he's a professor at Queen's, and Hao Han, who is at Microsoft. So feel free to reach to any of us if you have any questions or if you want to get the source code and play with the ideas. So first of all, what is authorship analysis? So let's say you have a set of documents that you don't know the author of. These documents can be as short as a tweet or as big as a play or a book. They can be on different media like an SMS, or email, or a blog post. And you're interested in knowing some characteristics about the author. You might be interested in identifying the actual author, so the real identity. Or for some reason you can't identify the author, you would be interested in at least knowing some of the characteristics of this author. So characteristics could be like their gender, their age group, or their education level. So the authorship analysis problem can be in one of three settings. The first one is authorship attribution. In this setting, you have a closed set of candidate authors. So you have your anonymous text and you have a list of people who might have written this text. And your goal is to identify exactly who that person is from this closed set of candidate authors. So what you do is that you collect writing samples from each author of these sets, and you compare them to pick the most plausible author of this anonymous text. Now, some restriction on this problem, the larger the number of candidate authors, the harder the problem becomes. The more text you have, or the longer the text is, the easier the problem becomes. Now, when the size of candidate set is 1, we have a problem called authorship verification. So in this case, we also have an anonymous text, and we have an author who claims to have written this anonymous text. And your task is to say whether these, let's say you have a sample document from this author, and your task is to see whether these two samples are written by the same author. So one very common application on this setting is plagiarism detection. The third, by the way, although this has one author, this might seem as an easier setting than this one. It's actually harder, because in this setting you have for each author a positive samples and negative samples. So you can see this is his writing, his or her writing style, and the other samples contain not how they write. In verification, we only have examples on the positive samples, so it becomes a very harder task. The third setting is when either we are not interested in identifying the actual author, or we cannot identify a closed set of candidate authors. So we resort to knowing some characteristics of the author, or generating a demographic profile for the author. So similar to the same problem, instead of having authors, we have attributes. So the gender, or the age group, or education level. And we have writing samples where each sample is labeled with one of these attributes. And you have your writing sample. You analyze all these documents, and then the process becomes to label this anonymous text with one of these attributes or all of them. So all these settings are very similar. They all focus on the writing style, but for this talk, I'll be focusing on only one setting, which is the authorship attribution or identification. So both names are commonly used. So the most common component of these settings is the writing style. So first of all, what do we mean by a writing style? So researchers have identified, let's say, the habits of the way that we write our documents. And they reached to an agreement where, similar to having a fingerprint, each one of us have a write print, which means each one of us has their unique writing style. So how does this happen? So we're writing a document. We're in the process of writing a document, regardless of what it is. And usually we have a topic in mind, or an idea. Given the limited size of the document and the capacity of language, we usually can speak about a certain topic using specific ideas, and the same idea can be expressed in different ways. And this is where the author bias shows up. So I might use one synonym, you might use another one, and this is how we have a different writing style. Also, in terms of the content or the structure, we sometimes start by certain greetings. Others would use no greetings, or their own unique greeting. You might even notice this among your friends or your colleagues, that they have their own greeting line, or they use certain words more commonly than others. So these are the features that represent our writing style. So these features these marks could be intentional or unintentional. The intentional ones are, as discussed, you have your own bias. You're exposed to certain words, or you like to start your sentences in a certain way. And there are unintentional habits where you would end your sentence with a period, or you don't use it, or you end up with 2 new lines between paragraphs, or you tend to write longer sentences versus shorter sentences. All these are things that we write without being aware of. And authorship attribution or writing style can be captured by looking at these features. So these features have been around since 1880 something. The problem is not new. It has been investigated a lot. And because of that, the features have evolved from starting by function words. So researchers said we're going to use function words as representation of the writing style. So those type of features are handcrafted. Someone comes and say, I'm going to try these features. They propose them, they run their experiments, and they show higher accuracy. So the way they're collected is that you have your document, and you have the feature extraction process, and you convert this document into a matrix of features and documents. So this is one way of doing it. So each document can be represented as like its own features or its own writing style, a variation of an author writing style. Or you can just combine all the documents from one author and create one author profile using the same features. So next, I'm going to show an example on what features are, just quickly. So on the character level, you can take ratios of, you can count the characters and then take ratios of digits to characters or letters to characters, uppercase, tabs, etc. Or you can look at the word level, like count the words, take the average sentence length, average word length, etc., etc. So those are referred to as static features, usually because beforehand you decide what features you're going to use in your problem, and you just look for these features in your document. We have different types of, like, more commonly used these days, that are called the n-grams features. I'm sure you're aware of these. And for authorship attribution, n-grams can be done on the word, on the character, or on the part of speech level. So if we have an example like it is noticed and appreciated, these would be examples on 1 to 3 n-grams. So it or it is, no or not, etc., etc. So let's focus a little bit on authorship attribution. Again, this is the setting that we have. It's commonly treated as a classification problem. You can do it as a profile-based problem where you generate a profile for each author, and it calculates the similarity between the document and the profile. But it is mostly used, like, it's most commonly treated as a classification problem because there are some features that cannot be combined, like categorical features. It's easier to keep them on the document level. And also, it might be easier to find similarities between two documents rather than a document and a complete author profile. So the same process, the author's names are the classes, and you have instances from each document. And the writing styles are extracted from both the documents and the anonymous text. So I'm going to show here one specific example on a tool that was developed by our group. We have 2 papers on this. The papers are called Visualizable Evidence-Driven Approach for Authorship Attribution, and the other version is on Arabic tweets. So the way this problem is usually approached is that you have a document, an anonymous document, and you have your writing samples, your training data. You train your model, you calculate its accuracy, and then you predict an author. So this is a traditional outcome for an authorship attribution problem. You say that we think it's author 2, and our confidence is 92%. So if we focus on the application of this work, as we said, this has been investigated in the literature. So recently there has been a study that showed that some of the work that was done by Shakespeare was actually co-authored by Marlowe, who lived at the same time. And researchers used authorship attribution techniques to compare the writings of the 2 prominent authors, and found that 3 out of the 8 plays are actually co-authored by Marlowe. So they should not be completely attributed to Shakespeare on himself. Yeah. So while this works for something in the literature domain, authorship attribution can be also used in a crime investigation, where an officer of the law wants to decide whether an anonymous message or a threatening message is sent by a specific author. And the way it works in court is that they bring a domain expert who is an authorship attribution expert, and they have to present the results in court for the members of the jury. They cannot just present these two values or try to explain support vector machines to members of the jury. They have to convince them why this is actually accurate and why it works. So what we have done is that instead of just showing the label and the accuracy, we extracted the features from the authors, and we project the features representation on the investigated document. So this is the same document that we have. Each line represents, so each sentence is represented with 3 lines. The first line is the character level, and this is the token level on the sentence itself. And the line below is for the part of speech tags. And the contrast in the colors shows the similarity between the writing sample of the author and the investigated document. So I think even without me explaining to you what's happening in here, you can probably tell that this darker color indicates something in here, indicates something in here, and indicates another thing in here. And you are probably correct. You are definitely correct. What this is showing is that candidate 2. So if we're saying we have 2 candidates, candidate 2 uses this word, guys, so many times that it appears in this investigative document as a very dark color. They use the word teams. It appears a lot organization. And on the part of speech level, they used a verb followed by and a lot. So now we can explain the results to anyone who even does not have a technical background on authorship attribution. In addition to that, we have provided more information about the outcomes. So, for example, we showed the similarity score per author for each one of the features. And then we show a cumulative score, like every time you introduce a new feature and calculate the whole score, you see how we're reaching to a more concrete decision about who the author is. I couldn't find the demo, so I had to pull up some figures from the paper. So sorry for if there is any confusion, because we're using 3 authors in here. And finally, we show the confidence score in our algorithm. So anonymization and obfuscation. So using authorship attribution for, let's say, non-controversial applications was fine. It's very useful. We can see the benefits of such applications, but it can also be used with the same setting to, or maybe misused to be precise, misused to reveal identities of people who don't want their identities to be revealed. For example, if you have a whistleblower who wants to reveal secrets about their company, but they don't want to be fired, or in under regimes who oppress freedom of speech, they want to persecute people who speak against the government. So the same setting can be used to uncover the identity of these people. So there has been more work on anonymization to protect these people, to hide the identity of the authors. Also, from the perspective of understanding authorship attribution, this is a very important task that can help us understand what is authorship attribution, what is the writing style, something that many authors currently struggle with. So we have an adversarial task that can be used to hide the identity of the author or hide the writing style. And then we can use these techniques to understand what is being hidden, to understand what is writing style. So the structure of this problem is exactly the opposite. You have an author who wrote a tweet, and then you use the anonymization technique to hide their identity while preserving the content, so that you cannot find who the actual author is. And interesting enough, the way to measure this is by applying authorship attribution technique and measuring the drop in the accuracy. So I think I'm a little bit behind in time, so I'm going to be a little bit faster in this. Some of the interesting tools on anonymization. So anonymization can be done using basic generic tools that are not intended for anonymization. One example is back translation, where you have a sentence that is written in a certain language. For example, here we have, how is it going, bro? This is in English. And then you translate it to a number of languages, then back to the original language. So from English to German, then from German to French, and finally from French back to English. And here we see that this is the same sentence rewritten in a different style. So this is one of the ways to do authorship attribution. It's one of the weakest ways, to be more specific. A more advanced technique, let's say, is a rule-based data augmentation techniques, where you have a sentence and then you have replacements or modifications on these words. So you pick a word either randomly or using some rules, and you use synonyms to replace these words. I'm just gonna skip over these and move to more interesting ones. Now, for the task-specific tools, this is one of the more recent tools. It's a heuristic-based authorship authentication. You have also rule-based techniques, but you want to reserve the content as much as possible. So you have a cost for each change that you do. So let's say character flips. This can ruin the sentence, but humans can still understand if you have few typos, and this has a highest cost. So you build a tree structure, and the goal is to find the least the path with the least cost with the most changes in the text. Finally, this is one of the most recent papers that was done in our lab. This uses generative models, and it's called embedding rewards using autoencoder. So the base of this model is an autoencoder that is used to train on a text and then regenerate a text. It's very similar to back translation in some sense. The difference is that we want to encourage the model to generate new words from the new sentences. So the best thing that a model can do in a generative model is to replicate the original document itself. This would give you the best reconstruction loss, or the lowest reconstruction loss. So what was used here is reinforced algorithm from RL, where we added an embedding reward loss, where the algorithm is encouraged to explore other synonyms and use them in the generated sentence. So just like in RL, you want to encourage exploration versus exploitation. So you want to see the most similar words being selected to the word that you want to replace. And also you want to encourage the model to explore. And that's why we use the most similar words to the synonym to be replaced, and the random case words to be replaced. So the paper is just being published. It's by Hao Han, and it was accepted to NACL just very recently. So I'll invite you to look at the details in the paper. I'm just going to show you a sample on generated text. So this is one random sentence. Maybe I just missed this point in the proof. And here we have a set of baselines. Syntactic term frequency does the anonymization on the vector. So after you extract your features, anonymizes your vector, your feature vector. And if you look at the words are completely unrelated to the original sentence. So this causes a problem, because if you only evaluate the authorship, the drop in the authorship attribution accuracy, you'll see a large drop. Now, of course, this is a valid method. So they evaluate this task for classification. You can still do classification using this method, but you cannot infer the ID of the author from the feature vector. But if you look at the generated content, it's very poor. Random replacement is that you pick random words and you just replace them with other words in the content, in the context. The goal is to break n-grams mostly, while preserving the main idea. So usually when you want to publish crucial information about a company, you don't really care about how eloquent you sound, but rather sharing that information with the public. And this is what random R does. Autoencoders with some guarantees on differential privacy sort of does well, but also it is in terms of the content, you can see some random words appearing. And the best method that, of course, like this is why we're showing it, because this is our results are the best. Maybe I just missed this restoration in the proof. So you see there is some variation, but in terms of the content, this has the highest level of content preservation. With 1 minute remaining, I'm ready to take questions.
Thank you very much for your exciting presentation.
Thank you.
So now it's time for the audience to ask questions. But before we start, I have actually 2 questions that I wanted to ask. So at the beginning of your presentation, you mentioned that the increase in the document length helps in authorship attribution. Could you kindly elaborate to that part, why it's helpful in that domain?
Sure. So basically what we're saying here is that if you want to extract the writing style, you want a larger text so that you can have a meaningful representation of the style. So in some cases, even a short tweet can give you an indication of who the author is. Like if we say totally fantastic, you'll probably think of Donald Trump. Or if you think of the sentence, let me be clear, this is a sentence that Obama used to use a lot. But for normal people, if you say something like, I hope you guys have a nice day, you don't have much text to work with to extract these features. These are like very generic sentences or very common sentences. It is hard to find enough representation of the writing style. Versus if you look at a book, for example, or a play by Shakespeare, you can easily find enough text to work with to capture or to see a variation in certain features compared to other authors. So that's why the length of the text is important. Also, if you have more samples, this becomes like just like any text classification problem. The more samples you have for training, the better you can do the attribution problem. So some of the tricks that you can work with if you have so many samples but very short text is that you would combine a few of them. This is what we did for Twitter. So we combined 5 tweets together to create one synthetic tweet for each author. And we showed that this gives you better performance than just looking at each tweet separately.
Okay, thank you very much for your explanation. So we have a question from Fabrizio. Please go ahead.
Thank you, Malik, for your presentation. I have a question. At the very end of your presentation, you show an example of a kind of obfuscation that you perform. I'm just wondering, how does one evaluate an obfuscation? Because yes, the authorship is difficult when you corrupt the sentence in that way, but you also have to measure if the point, the information is faithfully transmitted by the end result. For example, in the example that you show on your slide right now, there's a shift in semantics that is quite important from the initial input to the output of your system, so much so, in fact, that the end result is barely understandable or has very little relation to the original input. So could you explain how one evaluates such a system? Is it completely automated? Is there a ranking that is manually attributed to the output?
Yeah, sure. So this is actually a great question. So there are 2 points you're asking about: how we evaluate attribution and how we evaluate the semantic similarity. So it's important to note that humans cannot do this task. So from the early 60s, a naive base with the function words can outperform humans on this task. So this partially answers the question is, can human do evaluation on this? The answer is no. So all the evaluation for these techniques, either on the semantics level, the syntax level, and on the authorship attribution level, are both done automatically. Now for authorship, for like the identification, the performance accuracy, the evaluation is done by authorship attribution. You have your text before anonymization. You do your attribution. You try to identify the author, and then you anonymize it, and you do the attribution again, and you see that there is a drop in the accuracy by 20%. So you say this algorithm is 20%, like the efficiency is like dropped by 20%. In terms of the semantics, there have been different ways in evaluating this. All of them are based on automatic evaluation techniques that are borrowed from other tasks. So one way is using it's called universal sentence embeddings by Google. So you calculate the sentence embedding before anonymization, and then after anonymization, you calculate the distance using maybe the cosine similarity. And if you see that the difference in the cosine similarity is low, or the lower the difference in the cosine similarity, this assumes that you have preserved the content. Another way is using blue or rouge that are used for summarization and translation. They are being used to evaluate the content preservation. Now, this obviously is flawed, but these are the current techniques that are being used to evaluate the sentence.
Okay, I understand. But just to add a small point, I think it would be very interesting to sample 100 outputs and try to measure manually what kind of semantics similarity there is to the input, to get a sense of the faithfulness of an anonymization tool like the one you present. Otherwise, with automated metric, it's very difficult to get an actual sense of that element of the quality of your system. But thank you for your answer.
Of course, I completely agree. Yes, so the problem with these automated measures is like it's clear in other domains as well. Just like people criticize it in maybe less in abstractive summarization. The one issue with this approach, it's not an issue. Like it's a good suggestion, but it's going to be hard because every time you have a new anonymization technique, you have to generate the sentences, and then it's going to be hard for humans unless the difference is clear, just like in these examples. It's going to be hard how you would rank these sentences. So I'm expecting this to be very messy, but it's definitely better than these artificial measures. Yeah.
Thank you.
Pleasure.
So thank you. Another question I can see from Elizabeth.
Hi, yes, thank you. Thank you for the talk. I had, well, two different questions, but I can just ask one. I was curious whether you are in both of these systems on both sides, whether you are looking at a variety of different text types, like, all together, because I would think that would make a pretty significant difference. Like, if you're comparing tweets to tweets, or you're comparing, in the Shakespeare case that you were given, plays to plays, but for one person, the way they write, if your corpus is composed of the ways they write tweets and professional emails and a variety of things, I mean, do you separate those out, or what do you do with them?
Yeah, so usually these are treated separately. It definitely can be done. Like if you have generic features, you can definitely extract them from, like n-grams can be extracted from tweets and emails and etc. But it has most commonly been not the case. So you would focus only on one genre or one domain, and the problem is that, or the reason is that, authorship attribution at its current stage is still hard. So we don't even have higher accuracy. And if you put on different modalities, it's going to be even harder for the attribution technique. So that's why mostly it has been done on one modality level. So either you collect the same tweets or you collect the same emails, because you don't want, we know how these machine learning techniques, they pick up on any small detail in the text. So you don't want the for example, the author to be chosen just because he has written an email and we're investigating an email. So there are these like subtle details that we are not even aware of that could be picked up on by attribution problem or attribution technique, and could like attribute the author by mistake just because they are on the same domain. So in fact, like the topic, like even in the same domain or the same media, the topic is currently a huge problem for authorship attribution, because all these techniques, they pick up on the topic in your document, and they tend to pick the document with the highest similarity based on the topic rather than the writing style.
Exactly.
Yes.
Well, so this kind of leads to my second question. I mean, about guarding against, false positives, if you will, or in the other direction. You said something about it being kind of known or taken for granted that that people do have. You evoked like a comparison to a fingerprint or something of a very unique writing style. And I mean, for certain people, I'm sure that's true. But what are you basing that on? Given that we don't have a central repository where a huge portion of the population has been tested for things like that.
So the basis of this is that people just collected, like, not in the sense that it's but the setting is that if I take some of your writing samples and I just pick one random sample from these, then collect a few samples from your colleagues, I'm going to predict, like, not me personally, I mean, the attribution problem is going to pick you as the author with very high confidence. Now, this is giving that we have enough writing samples from you, so at least 20. So commonly the numbers of samples is like 20 plus, and enough text in each sample, then you would be surprised how effective these techniques are.
Well, but effectiveness is different than having ground truth data for a population.
Oh yes, yeah, we don't have that. So you can just take a random person and just pick him exactly. You need to have that thing. So maybe if that gave the wrong idea when I said right print, but what I meant to use it in is that you have your own unique writing style, and it can be extracted from your document. Now, we might not have access to that. Well, on the internet now, we might have access. No one has officially or openly done it. I'm not sure, but yeah, it is. So I guess maybe this is a tangent a little bit to your question, but one of the reasons why I wanted to talk about this is to bring to the people's attention how important is this problem. Because we write on the internet, sometimes we feel like we're protected by the anonymity of the internet, but we're actually not. So even if you have a Twitter account, I would probably guess your identity by just going over your tweet.
Yeah, I think I completely agree. It's a very important issue, in that people aren't as anonymous as they think in their writing style. But I think especially in applying it to real legal context, like you were evoking expert testimony, I feel like that's a place where we need, personally, I feel like ethically we need to be slightly more careful about the application, especially given that we know that a lot of the things that the computational stylometry is picking up on, like you say, are things that people can easily manipulate themselves, even intentionally. Or for using tools for anonymization. It's like, is that really what we, do we really want to convict somebody on the basis of the fact that somebody could have falsified in their name, their text?
Yeah, I completely agree. Yeah.
Very, very, very interesting. Thank you.
Thank you very much.
Thank you very much again, Malik, for your presentation and answering questions. We need to move forward to the second speaker. We have, as I mentioned earlier, we have Jonas Pfeiffer, who is joining us from Germany on the topic of adapters and transformers, a new paradigm for transfer learning. So first of all, thank you for joining us, Jonas, and the floor is yours.
Yeah, thank you very much I have to give permission. I have to close.
I assume Jonas had a Mac computer because of the permissions that you mentioned. So we're waiting for him to join back. Are you here? Okay, great.
Yes.
So
can you see my screen?
Yes.
All right. Yes. Cool. Yeah. So thanks for the invitation. My name is Jonas. I'm a third-year PhD at the Technical University of Darmstadt, where my PhD thesis is investigating different applications of adapters in transformers in natural language processing. So today's talk will involve some of my recent work, as well as some outlooks and new possibilities of how adapters can be used and different architectures for that. So my promise of what you will learn today is, first of all, a brief introduction into what adapters and transformers actually are. Then I'll briefly go into detail on the efficiency of adapters compared to normal fine-tuning. I will introduce to you adapter fusion, where we compose and leverage the information of multiple adapters that are available for transfer learning, as well as a stacking approach for adapters for zero-shot transfer to unseen and low-resource languages. In the end, I'll introduce to you the Adapter Hub framework, which allows easy training and evaluation and sharing of adapters built on top of the Hugging Face framework. So in general, everything that I'm about to cover involves transfer learning in NLP, where I'll only focus on transformers, which has been pre-trained on math language modeling, and normally we fine-tune the entire model. So in adapters, it's a bit different. So first, let's look at normal fine-tuning. So if we have a transformer, then we usually fine-tune all the weights, theta, on our downstream task, given the data set and the corresponding loss function. With adapters, it's a bit different. There we actually pull apart every single layer of the transformer and add new adapter weights. So we define those as phi. So we have theta and phi, and the adapters are encapsulated between these transformer layers, which we actually freeze. So that means we no longer fine-tune the transformer weights. We only fine-tune the parameters of the adapter phi. So what do we mean by encapsulation? So in general, what we're trying to do is learn a transformation of the underlying model that it's more suited to our new tasks. So for example, if we do language modeling, then we would fine-tune the adapter on an English corpora using math language modeling, and another adapter, for example, on Quechuan. But because the input representation of both for both adapters come from the same transformer model that are frozen, and because the adapter has to learn a representation that is or adjust a representation that the subsequent frozen layers accept, that we can assume, or we assume, that these adapters are actually roughly interchangeable. So because they're stitched in between frozen layers. Okay. So, but first of all, let's look at the general performance of adapters compared to full model fine-tuning. This is primarily based on work by Neil Holsby, which was presented at ICML 2019, where they already showed that this parameter efficient fine-tuning strategy with adapters performs on par with full model fine-tuning. And this is what we see here. So there's two different architectures. We propose a slightly simpler one where we only have one component. Holsby has two components within every adapter, but all approaches perform quite well. Sometimes adapters are better, sometimes full model fine-tuning is better. So yeah, the performance is quite good, even though only a very small amount of parameters in contrast to the entire model with full model fine-tuning is trained. To take that into perspective, what we're primarily working with is a compression rate of 16. That means the bottleneck of an adapter. So adapters usually have a down projection and an up projection at every single layer. So you can kind of define the capacity of the model based on this bottleneck, and with a compression rate of 16. So that means we have dimensionality of 48 within every layer. That amounts to roughly 900,000 parameters and requires only the storage of 3.5 megabytes. So that means storing roughly 150 tasks requires the same amount of space as two fully fine-tuned models, allowing you to basically add all tasks into a single model without having any problems on your server. Okay, so in Adapter Fusion, we're trying to leverage this information for transfer learning, and this is going to be presented at EACL this year. So here we're tackling multiple different problems. First of all, in multitask learning, we usually have the problem of catastrophic interference as we share the entirety of parameters, and the problem of sequential fine-tuning, where we continuously update the model, results in catastrophic forgetting because we forget information that was learned at earlier stages. So in order to mitigate that, we propose to first train task-specific weights, in this case adapters, so that no information can be overwritten and thus forgotten. But also because every single task has its own parameters, there's also no interference between these adapters. And we propose to combine these representations subsequently. So again, assuming that these adapters are somewhat interchangeable, we propose an attention mechanism given a pool of adapters. So in this case, we have 3 pre-trained adapters trained maybe on NLI, sentiment analysis, and some common sense reasoning tasks. And then we leverage an attention mechanism that automatically and dynamically learns to look at what, or tries to learn to weight the representation of the respective adapters that we have available. So we define the input to each of the adapters as the query and the output as the value and key, so that the dot product of key and value learns to dynamically weight every single adapter. So at every single layer of the transformer, we have a set of adapters available, and the model learns to automatically identify which of these adapters is the most useful for the downstream task. And we see that high resource language tasks usually just leverage their own adapter. So for example, multi-NLI. So in this heat map, the y-axis are the source, the target task that we train on, whereas the x-axis is the pool of adapters that are activated. And these are the activations of adapter fusion at the respective layers. And the diagonal means that the adapter just used, the model just used its own adapter again. So high resource tasks just leverage their own adapter, and thus the performance is on par with as to just fine-tuning the normal task with a single adapter. But lower resource tasks tend to leverage these high resource adapters. So for example, down here, we can see that the task CB combined the representations of multi and align and QQP. So there's like a weighted average across that. And at different layers, different adapters are activated, which again kind of shows that adapters are in fact modular. And when looking at the direct comparison to full model fine-tuning, here we present the results of the lower resource tasks. We can see that, so this is the delta compared to full model fine-tuning. And we see that some of the low resource tasks actually already perform slightly better. Some are on par with full model fine-tuning. But we see that for all these lower resource tasks, the fusion, which leverages the other tasks as well, outperforms the single task adapter. Okay. So this is one way to compose and leverage the information of multiple stored within multiple adapters trained on different tasks, and let the model kind of decide which adapter is necessary or helpful to solve the downstream task. We have some more results in the paper, which due to time I've mitigated. We also experiment with multitask adapters and so on. So I'd point you to the paper to look at that. But in general, the pattern is the same thing as what I've explained with single task adapters. So the next thing that we looked at was stacking of adapters. This is for multitask cross-lingual transfer. So in zero-shot transfer we usually start with by pre-training a massively multilingual model on huge amounts of data in multiple different languages using vast language modeling. Then we leverage this model, fine-tuning it on a task in our high resource source language, and evaluate it on the target low resource language. And this is extremely important because getting training data is quite expensive, especially for languages that we consider as low resource. So as all of you know, there are a bunch of massively multilingual models available, such as multilingual BERT and XLMR, and they actually achieve state-of-the-art results on cross-lingual transfer. The problem is that they all suffer from the so-called curse of multilinguality, where the performance especially deteriorates on low resource languages and ones that are not covered. So basically, the problem is that we cannot represent all the 7,000 languages that are available in the world in a single model. And we propose to, in our approach, to leverage these multilingual models, as we assume that due to their massive multilinguality, they're still kind of the best grounds for transfer learning to unseen languages. And this is where we propose MADX, where we train adapters for languages and for tasks. Languages include ones that we have seen during training, but especially also ones that we have never seen during pre-training. And by stacking them, I'll get into detail about what that is in a minute. We assume that we can learn somewhat language agnostic task adapters. Okay, so in MADX, we start first of all with training language adapters. So as I've initially before explained, we can train language adapters, for example, on Wikipedia in English, and another set of adapters in Quechuan. So now we have two sets of language adapters. And in the second step, we stack task adapters, such as named entity recognition, on top of the language adapter. And because in the next step, we actually want to replace the language adapter with our target language, we don't only freeze the transformer weights, but also the language adapter. So in this setting, we only fine-tune the newly introduced adapter weights for the task, in this case named entity recognition, on an English data set. And in the third step, we actually replace, so for zero-shot transfer, we replace the language adapter of English with the target language adapter. So during training, we pass it the representations through the shared transformer weights into our language adapter, fine-tuning the task adapter, and during inference, we replace it with our CLIQ-ai adapter, but to retain the task adapter that was learned on English data. So the idea is that because we've had this language adapter stack before, there's no need to incorporate too much information of the English language in this task adapter, and that it's somewhat language agnostic. There are new strategies to do that, which we're working on, but this was like the first assumption that we made. So we evaluate this on 16 different tasks of different data set size. Some are covered by pre-training, some are not. They all come from different language families. And we evaluated on NER, XQuad, and XCOPA. I'll only go into detail of NER for now. So this here is the relative F1 improvement of our approach over the standard XLMR large transfer learning. So that means XLMR is fine-tuned on the task data in the source language and evaluated on all of the target languages. In this heat map, the y-axis indicates the source language and the x-axis the target language. So that means, for example, here, this score would indicate the transfer performance when training on English and evaluating on CLIQ-ai. And this is the relative improvement of our approach over the baseline. So we especially see that the top right-hand corner is actually the most realistic scenario as we transfer from a high resource language to a low resource language. The other quantiles of this matrix are more of academic nature, as you probably would not train a model on CLIQ-ai and evaluate it on English. But in this realistic scenario is also where we see the largest gains in transfer performance with our approach. There are some new updates on this in a more recent paper that's available on arXiv, which I cannot discuss at this moment. Yes, so this is one way to kind of stack adapters for zero-shot transfer to unseen languages. And now we've also had a brief study of the efficiency of adapters. I won't go into too much detail about this right now, but the general concept is that training adapters is a lot more efficient, where we get speed up gains of 57%, because we don't have to backpropagate through the entire model. During inference, it's a bit slower because we have additional components. And in this paper, we actually have some proposals of how we make this even faster, where we have a dynamic selection of adapters that, depending on the capabilities of the server and how many queries a server gets at that moment, you can dynamically select the how accurate the adapter should be and how fast the inference should be performed. But in general, adapters train a lot more efficiently. At inference, they're only slightly smaller. We have a lot less parameters to store per task, and thus we can add a lot more adapters or task to our server or GPU at the same time, which is not possible if you would do full model fine-tuning. Lastly, I would like to introduce to you the Adapter Hub. This is our framework that is built on top of Hugging Face transformers. And here we actually have very simple training scripts where, for example, if you have a normal Hugging Face training script available, then you just need to add 2 lines of code. So add adapter and then train adapter. Train adapter then freezes the transformer weights and only fine-tunes the new task adapters. So this is very easy to use if you're already working with Hugging Face. We also have some collab scripts and also inference collab scripts that you can play around with. But we also have the possibility for you to use the adapters that have been pre-trained by the community or by us. So, for example, if we look at one of those tasks, you can select which architecture you want to use, so BERT base, Distill-BERT, Roberta, and so on. And in each of those adapters, we then provide you with a short snippet how you can add this adapter to your model. We also have BibTeX files who train the adapter, what paper was used, what specific architecture. You can download them and so on. And we even have an automatic Twitter bot that when you upload one of those adapters, our Twitter bot will automatically tweet about your awesome new adapter that you have made available to the community. The same goes for language adapters that we've kind of incorporated in the MADX paper. So here are a lot of pre-trained languages that we have available for you to immediately play around with. Cool. So to finalize this, there's been some recent work on alternative adapter architectures. So there's diff pruning, where you no longer actually fine-tune any weights. Well, you do, but you learn the difference to your adapters in a sparse matrix. There's BitFit by Yoav Goldberg's group that proposed to only fine-tune the bias terms. There's prefix tuning by Percy Liang's group that just trains a prefix that is preset to every single input, which is also a type of adapter. And there are a lot of different questions that are still open. So we've in our adapter fusion approach, we've kind of proposed a quite simple and straightforward way of combining the representations, but there are definitely more better ways to go forward. There are domain adapters that might be explored. There's ideas of hypernetworks and CPGs for adapters, for example, in UDapter. And in general, I think a good direction would be to increase the modularity of adapters, as this is a quite exciting direction to combine the information stored. So the key takeaways are that adapters train a lot faster than normal fine-tuning. They're modular and can be stacked and fine-tuned sequentially, which is especially helpful for zero-shot transfer. But they can also be leveraged to compose and combine the information in a non-destructive transfer learning setup. So thank you very much for your attention, and I'm open for questions now.
Thank you very much, Jonas. Very exciting presentation. I personally have quite a few questions that are written here, but first I would like to give the opportunity to the audience to ask questions. So do we have any questions from the audience? Okay, so if not, I'll start with my question. So in the last slide in section 1, I was a bit confused. I'm not sure if I saw it correctly or not, but I kind of felt like using a lower compression rate results in a higher size for the final adapter. I'm not sure if I saw it correctly.
Yeah, so I'm not happy with the definition anymore. This was, so the compression rate means this is the dimensionality of the transformer divided by this compression rate.
I see. I thought this is the number of the what is it, the compression layer. Okay, thank you for clearing that part. So the next question that I have is about adaptive fusion. So if we want to include adaptive fusion in a continual learning scenario where we just have a new task, or we just have tasks that are sequentially added to the model. So in that scenario, how would adaptive fusion work? So in that scenario, would we need to retrain the fusion component once every new task is added, or how would we need to treat that part?
So we haven't explored that yet, what happens. We have some preliminary results on that it is possible to just add the adapter to the pool, and that it selects the correct adapter, even though it's never seen that before. So that's a definite plus over normal multitask learning, because the information can be leveraged and extracted automatically, even though it hasn't seen this before. But we haven't looked at that in detail yet. So it's technically possible. I think there are ways to make adaptive fusion, the adaptive fusion layer, robust to such settings. But it's an open research question. So from the implementation side and from the theoretical point of view, it is possible. So you can technically train adaptive fusion with only 3 adapters and just throw in 100 others when they become available. So that is technically possible. How well that performs needs to be analyzed more thoroughly.
I see. So thanks. In a few slides after, there was a heat map over the attention weights. Yeah, this one. So my question was that, why do you think the weights are more scattered if you go operate in layers?
Yeah, that's also a very good question, and we've only found the answer to this question quite recently in our newer paper. That's basically because if you look at the transformer, then let's look at this kind of setting. So we're assuming that that the adapter is encapsulated between multiple layers, right? Frozen layers. And so this transformer is just copied and pasted, for 12 layers. And so these layers here are the output representations that is frozen for the previous layers and so on, right? So that's how adapters are frozen, are encapsulated between layers. The only difference is the last layer. And in the last layer, we don't have another transformer, obviously, but we have a prediction head. And this prediction head is completely fine-tuned together with the transformer, together with the adapters, right? So in a sense, this results in the adapter not actually being encapsulated between frozen layers, but it's more like an extension of the prediction head. So that means it doesn't no longer guarantee that these adapters are in fact interchangeable anymore. And so in more recent results, we actually found that when we just throw away the 12th adapter, so the 12th adapter meaning for base model in general, the last adapter in the last layer, the performance considerably improves in adaptive fusion, because then we don't have this scattering situation anymore. Yeah, so this is again an indication that because we freeze the surrounding layers, this makes them modular. If we don't do that, things like this happen, and they're no longer interchangeable.
I see. So basically, that scenario only applies on the last transformer layer, rather than the thing that I asked, which is going up into layers.
Yeah.
For all the layers we have, we don't have the scatteredness. But
yes.
We only have it for the last layer.
Exactly.
Cool. Okay. And my last question would be that it's related to the Maddox paper. So my question is, does the use of language adapters require having multilingual language models in the first place?
In this specific scenario, yes, because we leverage the vocabulary of the pre-trained model. So if you would have a new language, so let's say you have, if you want to do transfer learning from English to Chinese or something like that, then the BERT vocabulary would not be able to actually represent the input text of Chinese. So that's kind of a problem. However, again, in more recent work, we specifically target that. Not in a sense that we want to leverage BERT, like a monolingual BERT, but extend a multilingual BERT to scripts that are unseen. So, for example, Amharic is not covered by MBERT or Tibetan and things like that. So in that paper, we propose approaches so that this also works. So technically, this idea, this approach can be applied to any language model which was trained on any language and can be transferred to any other language.
I see. So basically, in that case, the fact that the task adapters could be applied over different language adapters, is it correct to assume that it actually comes from the fact that our transformer is multilingual in the first place, and that is why the representations from the language adapters are kind of within the same feature space? And it doesn't actually come from the adapters themselves. It come like it's the same feature having like the outputs of the language adapters being in the same feature space. Then it comes from the transformer part rather than the adapters. It mostly comes from the transformer.
Well, we did compare to just normal fine-tuning, right? And there the performance is considerably worse. We also compared it to just replacing the task adapters, so not having the language adapters at all, and that also gave worse results. So I would say that the adapters adjusts the representation of every single layer in the transformer that it works better for that specific language. So we just give the model a bit more capacity to learn the idiosyncratic information of that's required for every single language. So I would say that it's a combination of both. Like there's an adapter is not very expressive. It's just a simple down and up projection. And only through the nonlinearity and the multi-head attention of the transformer does the expressiveness and this transformation of every single layer actually get its quality, let's say. So I think it's a combination. Like you couldn't use that for any other model. It kind of transforms the internal representation slightly that it works better for that language, basically.
Mm-hmm. I see. So in my opinion, it would be nice to actually look into because those language adapters are not explicitly they don't have an explicit objective of mapping into the same state space. So it would be nice to actually look into why it actually happens with the multilingual adapters. That, in my opinion, would be a nice thing to be investigated and better understand why they behave like that. Mm-hmm. So, yep, thank you very much. So that's it. That's the end of my questions. So now it's time for the audience to ask questions if they have any. So seems like there are no questions from the audience. Once again, thank you very much for joining us, and thank you for your exciting presentation.
Thank you as well.
It was a pleasure. And we are moving forward to the last presentation by Dr. Jian from University of Montreal and the Rally Group, who is going to present VGCN-BERT, Augmenting BERT with graph embeddings for text classification. So Dr. Ni, the floor is yours.
Okay, thank you. Trying to, can you see my screen?
Yes, we can see it.
Yeah, thank you for the invitation to this meetup. And well, this work is a work from a student. And the student is called Lu, and also another research associate, Pandu. So I put their pictures here, and I don't put them mine because you can see me now. So this is a work done in last year, and it is about the combining BERT with GCN, trying to do text classification. So I'm going to talk about a little bit the details of this model. So the basic idea is to try to combine the local information that BERT can capture from a document, from a text, together with the GCN, which can capture some global information between different words in a language. So that's the basic idea. And let me just frame a little bit the context of this study. The first idea when we studied this work was to detect offensive language on social media discussions, such as the hate language and so on. And then we moved to more general text classification problem because the same approach can be used to any text classification problem. But this is just to give you some background of this study. And then, well, I put some basics about text classification here, which may not be necessary, but just let me say a few words about that. We may use some traditional approaches where you have to design some features and incorporate those features into different models, such as naive Bayes, SVM, and so on. And more, we use deep neural models where you have a text, and the text is mapped into some latent space for representation, which is learned. And then based on that representation, typically you will use a multi-layer perception to do classification. So this is the typical schema. And for representation, we can use different approaches to map text to representation, such as LSTM or bidirectional LSTM or BERT. And in this work, we just choose BERT to do that transformation. So using BERT for classification, you have basically this schema. So you have a sentence or a text, which is first transformed into word embedding. And then each of this embedding is processed in the self-attention layer. And basically in self-attention, you will try to find some information from the connected words in the sentence and try to produce a representation for each token in the sentence at the next layer. And so once you do this in multi-layers, suppose you have 12 layers, then at the end you can see that more and more the tokens will aggregate the information from the neighbor words or from the words from the same sentence. And at the end, for classification, you just take the representation of that spatial token, which is typically used to aggregate the information from that node. Sorry. From there, you can see that the information that the BERT basically capture is a type of local information, because when you move from one layer to another, BERT will try to aggregate the information in the same sentence to produce an enhanced representation for different tokens. So this is basically to aggregate the local information from other tokens in the sentence. And of course, you can think about the different types of local information that it can capture. So it can capture some sort of semantic information as well as some sort of syntactic information. So we can see that both types of information can be captured somehow, but we cannot understand exactly how this is done. And what's missing in that approach is that we miss the global information in a language. For example, in a language, you can have the synonyms of some words, which may not be necessarily represented in the BERT representation. And it is also possible in a lot of applications, we may have domain-specific knowledge about the vocabulary. For example, when you use this word, then typically another word or the meaning of another word or another complex expression may be implied. And this type of domain specific knowledge is not incorporated into the BERT mechanism. And it cannot be fully captured by using just the BERT mechanism. So this is the type of information that we want to enhance, we want to incorporate into the BERT mechanism. So the idea is to use both local information and an additional global information that we capture elsewhere and try to integrate them into the classification schema. So that's the basic idea. And just give you some example to motivate the idea. We can see here one example of a movie review. So you can see that when you comment on a movie, you can say it's a bit smug and repetitive. And this documentary engages your brain a way few current films do. And if you just rely on the local representation, and typically you can see that there are strong words such as smug and repetitive, which are typically negative. So using BERT or using other mechanism, typically this review will be considered to be negative. However, you can see that there is a segment of sentence which expresses a very strong positive view about the movie. And this is expressed as way few current films do. But then no specific word per se is a strong indicator of the positive view, but the combination of them do. So what we want to do is to associate this expression or to guess that this expression is somehow related to the notion of innovation. And this is the type of connection that we want to capture from some global word graph that we will create. So this is what we call the global information that we want to capture. And once you can successfully associate it to the notion of then the whole comment, the whole review can be considered to be positive. Okay? So that's the basic idea. Then the next question is how we can capture those global information from a language. So the approach that we have taken in this specific paper is that we want to use BERT to capture local information, and we use graph convolution network based on the vocabulary, based on words. And we believe that this word graph captures general knowledge about the language. And there are different ways to create the graph network. So you may have WordNet or whatever manually constructed thesaurus. And in this particular work, we use a different way. We try to determine the word graph based on co-occurrences. So I'll go into more detail about that. So the BERT mechanism, I think I don't have to go through that because everybody knows. And well, we have a the first layer that will map the token into embedding, and then there are, in our case, 12 layers of self-attention mechanism. And at the end, we will have some classification class label produced by the final layer of classification. Okay? But as I said, the limitation of that is that the combination or the aggregation of information within BERT is limited to local information present in the same sentence. So here we want to extend that kind of a connection to consider different connections between words. And when you have a word connection, then it is possible to connect different words through GCN, which is a graph convolution network, which is one of the typical approaches of graph neural network. And this is a figure which is used in the approach of a text GCN, which is a special application of GCN, where you can consider that you have different concepts here. The O here are different concepts, and in this particular application, it is about the medical context concepts. The disease put here, and then you have different concepts or different words connected to those diseases. So you have heterogeneous graph where you have either document, you can consider here the disease as document connected to different words. And then through the graph convolution network, it is possible that the information flows somehow from one node to another through the convolution. So at the end, you will be able to enhance your representation. So for example, from this node, you will be able to create an enhanced representation and another enhanced representation for the word as well. And it is hoped that at the end, when you try to classify a document, looking at all the concepts that are involved in a document, so you have different words involved in a document, you'll be able to classify the document into different classes. So you can say this is this type of problem, health problem, or another type of problem. So this is an application of text GCN in the medical domain, but you can just imagine that this mechanism can be applied in general. So in general, we have different connections between documents. So just to frame in the text classification case, you may think that you have connected documents. So one document cite another one. So there are hyperlinks between documents, and each document will be indexed by a set of keywords that appear in that document. So this is the typical graph that you can imagine. And the problem that we see in this particular application of GCN is that we lose the sequence information from a text. Once you map a text into a GCN, typically we don't have anymore the information about the sequence of the words. So for example, if you input those two sequences of words into GCN, the result will be the same. However, if you read the sentences, they mean different things. So that's a type of missing information in GCN. However, we have typically the global information that reflect the connections between different documents or between different words. So this is an illustration of the general schema of GCN. So you have input, which is a connected graph, and then the connected graph will be will be transformed somehow into the hidden layer, and then followed by ReLU, some nonlinear layer, and that follows several layers, several steps. So you may have 2 layers of convolution, like shown here, or more. And at the end, you have a output, an output where the nodes are represented with enhanced information, enhanced embedding. So that's the typical case. Now, the idea of combining BERT with GCN or with other graph neural networks have been done somehow. And I mentioned a case of medical document classification, trying to determine what's the best medication from that patient, for example. This has been framed in the case of GCN. So all the information is put into a GCN into GCN as input, and then this GCN output is used as input to BERT, and the BERT will produce a classification output. But here, what you can see that the GCN does not capture the sequential information because you don't have that. You have the input features that do not follow an order, a sequence. So it is not possible for BERT to exploit the sequential information, which is typically the case for natural language analysis, but not in this case. Okay, so this is something that we notice for this combination. Sorry. And there is another combination which we call the vanilla combination. That is, you use BERT to produce some output, some representation from a text. And you also use GCN to produce another representation. And at the end, you will just combine them, concatenate the 2 representations, and then use it in a classification task. So those are some existing approaches. But now what we do is a little bit different. So the first thing that we do is to create the vocabulary graph. And as I said, it is possible to just use WordNet for that, but we use here the co-occurrences because co-occurrence may reflect some practical usage of words, and a lot of the words used in the same text may not be stored in resources such as WordNet. So more specifically, we use the normalized pointwise mutual information to detect whether 2 words I and G have a strong connection, and these will produce some weight, some value in this range, and we choose the connections which are positive or at some threshold to be kept in the graph. So this is how we create the vocabulary graph. And then the second step is to do convolution on the word graph. And this is a bit different from traditional GCN. In the traditional GCN, what we have is a matrix, which is A, representing the adjacency graph. And typically, when we work with the GCN, we assume that the documents are connected by this adjacency graph. So this is what I put here, a doc, which is a network of documents. And then you have a specific document which is indexed by some words, and this is represented by X. Now, what you want is to exploit the inter-document graph A doc together with the input document X, and you want to create some representation for each of the document at the input. So this is the HGCN, and the W is of course learned from the whole process. And what we notice here is that in the traditional GCN, if you want to work on a document, the document should be already in the graph. Otherwise, it is impossible to exploit the adjacency graph to use on that document. So from this perspective, it is a transductive learning model. That is, you will not be able to apply the same approach to new documents, and you have to put those documents already in the training set. Now, what we do is to not to train the GCN on the document graph, but on the word graph. So we assume that this word graph can work on any document in the same language. So it is a more general language property than a property associated with a document. So if we just retake this equation to the word graph, we have this kind of manipulation of matrix. So we have a graph about the words, and as at this moment, when we just work on a word graph, we don't have any input. So the input will be the identity matrix here, and we learn some weight at this moment. So this is a step of a word graph convolution. And then we use the input of a document to connect it to the result of the word level convolution. And that will produce some representation using the VGCN used on vocabulary. So this is one layer of convolution. And of course, it is possible to apply the second one. That is, you have the first layer of convolution, and then you use the ReLU operator, and then you use the second one. So this is a typical case of GCN. You apply 2 layers of convolution, and this is the case as well in our study. So that's some formulas about that, and to just show the difference between the 2 convolutions. The traditional convolution is done on the document network. So some information from other documents can be transmitted somehow to the target document. So in such a way that the representation of this document will be enhanced by the information collected from neighbor documents. In our case, we do similar things, but on words. And the idea is similar. If you observe that this word 2, is strongly connected with word 1, then some information from word 1 will be transmitted to word 2. That will contribute to create an enhanced representation for that word. So that's the basic idea. Now, I will talk about the integration of VGCN together with the BERT. So using VGCN, we create some information about the words, representation about the words that take into account the connections between different words. Now, how we can incorporate that into GCN, into BERT, sorry. So the idea is shown here. We have, suppose that we have a representation from the word graph for the words that appear in the document. So suppose that we have some sentence which contain just 3 words here, shown in this figure. And the first step is to identify this subgraph, sub-word graph, where we can see that those words appearing in this sentence are connected with other words in the graph. And then we do a graph convolution, and that will produce a representation of those words, but in different dimensions. So we have some dimensionality. And we will produce for this sentence some representation here, which will be concatenated with the word embedding that we get in a traditional way. So the representation will represent 2 parts. One is embedding, and another one collected from the word graph. And the next step is to use this enhanced representation in the BERT operations. So we have different layers of self-attention, And basically, the traditional self-attention will just pay attention, or each word may pay attention to other words in the sentence. But now we are allowed self-attention to also be applied on the representation obtained from the graph in such a way that the representation from the graph can play some role in the self-attention mechanism. So gradually, what we expect is that gradually we will be able to integrate more tightly the information from the graph into the BERT self-attention mechanism. So that's what we expect. And finally, at the end, once we obtain the last layer's CLS representation, we'll use that in a classification layer using fully connected network. So that's the key idea. So this tight integration is something that we designed in this paper, which has not been used before, and I will show that it is quite useful. So let me, I look for the time. How much time do I have?
You have about 3 minutes.
3 minutes, okay, just move up. So I will not summarize the approach and just show you a little bit about the experiments that we have done. As I said at the beginning, our intent, the initial intent was to work on offensive language, and we included 2 data sets here about offensive language. So one is Irango hate, which will try to classify text into hateful or non-hateful texts. And we have Fanta hate, which have 4 classes, normal, hateful, spam, abusive. But we also worked on general text classification tasks for sentiment classification, for about the movies, and for the classification of linguistic acceptability, trying to determine whether the sentence is well written or not. So those are different tasks, and we compare with the different baselines, which is the first one is traditional neural network, and we use the BERT representation and then connect it with a bidirectional LSTM to do classification. And we also use text GCN as I showed, or just the VGCN without the BERT, or just the BERT. And finally, a combination of the 2 representations that we produce at the end to put to a classifier. So those are the baselines that we compared with. And here are some embedding size we just set at 16. And for the neural, the pointwise mutual information, we use this threshold to filter the connections between words, and we use the whole sentence as window size. This is the page that shows some the main results. So we can see that in general, what we observe is that VGCN-BERT produce the better performance measured in weighted average F1 score, and those are the macro F1 score in some cases. That usually is better than other models, except this one. In this case, the vanilla VGCN and BERT works better than what we used by using a tighter integration of both the components. But what we can observe is if you compare this last line with VGCN, you can see the contribution of BERT, because in this case of VGCN, we just use VGCN. Now, if we compare with the BERT, this shows the contribution of VGCN. And in some cases, well, in this case, that's a small contribution, but you have a larger improvement here in some other cases. Okay. So globally, what we can see from this table of results is that both the VGCN and BERT can contribute, can play an important role in text classification. And by comparing VGCN-BERT with this vanilla version, we can see that in most of the cases, there is an improvement by using a tighter integration of VGCN within BERT instead of just the concatenated two representation at the end. Okay, so that's the key message. And this is just one example to show what's the impact of the attention on the attention mechanism. That is at the last layer, we just look at the CLS token to see how strongly it pays attention to different tokens and to different dimensions of the word graph representation. And we can see we compared several versions. The BERT version, of course, there is no attention to those dimensions because those dimensions are not there. So, but we can see that a lot to the word do at that layer. We can certainly discuss whether this is reasonable or not, but you can certainly say this is not the most important word in that sentence, but BERT will pay a strong attention to that word. Vanilla VGCN and BERT, we can see this type of green lines. And of course, as this representation, the word graph representation is not integrated into the BERT representation. So the CLS token will not pay any attention to that. But this representation will be later on added into the representation. And here, what we can observe with VGCN-BERT is that there is quite a strong representation, attention paid to this last segment produced by graph. And this shows that indeed this second segment of the representation plays an important role in the global representation because all those representation, all those dimensions will be aggregated into the CLS representation, the final representation. So this is just to show that indeed the added dimensions are very important. And for this particular example, as I showed, indeed we can see that the representations here produced by graph correspond somehow to the meaning of innovation at several dimensions. And how we can get this representation of innovation represented in those dimensions? Well, we just try to determine what's the strongest words that appear in the whole in the subgraph that we extracted from this example, and see what are the strongest words tokens that are connected to each dimension. And this is a way to project the dimension into the word space to make some meaning. So you can see that the first dimension from the graph is about the boundary, innovation, and possibly a lot of other things. And we just picked the two strongest terms here for each dimension, and a lot of them are related to innovation. And this is why globally the sentence will be classified as a positive because of this hidden innovation scenes that has been found. That's it. So globally, I just wrap up. This study is some investigation trying to extend the local information with some global information that we can collect from a word graph. But you can think that the same approach can be used with some other manually constructed resources as well. And we also investigated the tighter integration of global information into BERT operation. And this sounds reasonable and very somehow useful because we have a better performance than vanilla integration. That's it. Thank you very much.
Thank you, Dr. Ni, for your exciting presentation. So we have about 5 minutes for the questions. So do we have any questions from the audience? You can, yes, I can see that Svetlana has a question.
Hello, thank you so much for the talk. I completely overlooked this paper. It's actually super interesting, but I think I missed a few points about the approach. So you mentioned that the limitation is that the test document, so the words in the test documents should be overlapping with the ones that were created in the graph, right? So you create the vocabulary graph from the training set, or how is it constructed?
You talk about the traditional GCN versus word graph GCN, right?
So for this vocabulary GCN, you need to create the graph from the words?
Yes, exactly.
And the words are from the training set?
The word is from the whole collection. It's not from the training set, but you can assume that your test set will use basically the same vocabulary. If you use some word that does not appear in the training data, you can just remove that. So that's possible. So you do not ask the training data, you do not ask the test data to be part of the training process, because the text in the test set can be represented by the same vocabulary. This is the assumption.
That's an assumption.
Yeah, so the training data is just rely on the vocabulary that you observed from there, and you assume that can be generalized to any document.
Okay, and so you mentioned that these are words, but actually these are tokens, right? You need to use the same tokenization approach as BERT, right?
Mm-hmm. Right. Yes.
And so just the last question is, so I didn't understand about the convolutions. Do you do it separately for every time for different document you have different graph embeddings, or are they the same?
Yeah, good question. So we have a global training process that will be will use the whole training set to train the convolution. And once the convolution is trained, let me show the formula. Which one is that? Yeah, here you have. So suppose that we have the training process, and we know how to determine the weight matrix at this level, the first level and the second level. Then you just plug in some input. Suppose that you have a test document, the new input X here. You just reapply the trained weight on that. You don't need to retrain the whole process. And I mentioned that we try to apply that to a subgraph A here. This was the complete vocabulary graph in the training phase, but in the test phase, we don't need to go through the whole graph. We just pick the subgraph for the input training and plug it in to the process of this model to get the final representation. So this is the final representation here. So here it is true. This is a document that we have, and this theoretically you have to use a complete graph to do the convolution, but as we only have a limited set of nodes of the graph, we just use in the test phase, we just use a subgraph here to do the convolution.
And the subgraph is defined as the neighbors, the first swap neighbors of the words that appear.
Yes, exactly.
Okay, and do you have also pre-training? First you pre-train this embedding, and then for each input document you modify them. Yes?
Yes, there is a pre-training. The pre-training, you mean we have the word embedding, and the word embedding is a globe, I guess, in this work. We just pick the globe representation as the input embedding. And then there is a kind of a training for the graph convolution. And that has been trained on the whole training set.
Okay, thank you.
We may have time for one last question from the audience. Do we have any questions? If not, I may ask the last question, and this is, how would you compare your approach with the adjacency graph that you have created based on the vocabulary and the training data in comparison to having, like, for example, a dependency parse tree of documents as the vocabulary, as the adjacency graph that you're going to use, and have the weights in the GCN be trained jointly with the rest of the model, with the rest of the BERT model?
Well, I would say this is a different approach. You can certainly do a dependency analysis that tries to recognize some type of linguistic dependency, syntactic dependency, and that will capture a different type of information from the co-occurrence analysis that I showed here. So the idea to use co-occurrence analysis is that you are not limited by the syntactic connection. You can try to connect any type of words if they co-occur very strongly. So this is something that we use quite often to just do a kind of a robust analysis to connect different words. And of course, the same approach can be used to, can be applied to the dependency, linguistic dependency, but I'm not sure that the linguistic dependency will play a strong role here, because once you connect some noun with the adjective, that tell you a lot about the meaning of the text. What the answer is not sure. So people tried that, but the results are varies depending on the context. So there is no conclusion or consensus that this type of information is really useful for text classification. But in some cases, yes, but not in general.
I see your point. Thank you very much, Dr. Ni. We've reached the end of today's meeting. So first of all, special thanks to all the speakers for their exciting talks. And also thanks to everyone who attended this event and all the people that asked questions. So this wraps up today's event, and also today kind of wraps up the winter. So we have a spring ahead of us, and hope everyone can enjoy the nice weather finally after a few months of cold. So stay safe, everyone, and have a great day.
Thank you.
Thank you.
My pleasure.